Hi everyone, this time we're going to talk a little bit about drag and air resistance. Now, throughout this course so far, we have talked about surface friction, and when we've used our friction equation, we are talking all about surface friction. This is one object as it's slid across another object. But now we're going to talk about air resistance. Air resistance is also called drag, and it's the resistance as an object moves through a fluid. Now, why do we say fluid? Well, fluids, as you might know, are gases and they are liquids, and they can also be plasmas. Plasmas we're not going to get into. They're charged particles in plasmas, and the math gets really crazy, nutty, wacky. You have all, and I have all played with air resistance. I don't know about you. When I was a kid, I would put my hand out the window and enjoy the fun of just sticking my hand out the window when we were driving down the road. This is a cute, adorable puppy that's enjoying some wind resistance in her face. If you see a lot of high-speed athletes, whether it is bobsled or skating or skiing or bicycling, they are going to try and reduce and minimize drag. Notice this gentleman has an aerodynamic helmet on. He's got his body crouched low, so he is very, very aerodynamic and not terribly draggy. So sometimes we want to minimize drag, but here's a situation with a parachute. Parachutist is falling out of the sky. They want to maximize drag. They want lots and lots of air resistance so that they can land at very low velocities and they can kind of step out of the parachute fall. So drag can be useful and drag can be a challenge. So how much drag an object has, how much air resistance an object has, depends on a whole bunch of things. One, of course, is shape. One of my favorite vehicles to talk about is the ever popular UPS truck, because it is the most non-aerodynamic object you see almost on a daily basis. UPS truck is a big box with wheels on it, and it's supposed to haul cargo. It is not designed to be in high speed like this vehicle is designed to be high speed and very aerodynamics and shape. So shape has a lot to do with it. Surface area has a lot to do with amount of drag. If I have a little boxy shaped car like this cute little Kia, this little Kia has a lot less drag on it than the UPS truck. They're both kind of square, but this is a much smaller vehicle. It has a smaller surface area, and that's going to cut down on the drag. If you want something to have very low drag, you make it very aerodynamic, like a rocket or a bullet that is flying through the sky. And of course, velocity is a big influencer on drag. Actually, the force of drag is proportional to velocity squared. So I've got a cute child on a tricycle here and a gentleman who is on a high-speed bicycle. Well, the person on the high-speed bicycle is going to have massive more drag because his velocity is going to be very, very high. The cute child, force of drag is not going to be much because he's not going to get that crazy fast on a cute little tricycle. Let's talk about this a little bit. Because of the fact that force of drag is proportional to velocity squared, here's what this means. If you have 2 times the velocity, you're going to have 4 times the force of drag. 3 times the velocity, you are going to have 9 times the force of drag. So what that means is a small change in velocity is going to make a huge increase in drag. Now there's a thing that is called terminal velocity, and it is achieved when a falling object has stopped accelerating due to the effects of drag. Basically, an object is falling at a constant velocity. How in the world does this occur? Well, let's talk about a parachutist who's just jumped out of an airplane. When a parachutist just jumps out of an airplane, the only force on this parachutist is going to be gravity. Because of the fact when somebody just departs the airplane, their original vertical velocity is going to be 0. But as they fall further and further and further and further, their velocity is going to increase. And remember, force of drag is proportional to velocity squared. So as the person falls and their velocity gets bigger, their drag vector is going to get bigger. Well, as they fall further, their velocity is going to get faster and faster and faster. And because that velocity squared is proportional to drag, if they are allowed to fall far enough and for enough time, they can get to a situation where the force of gravity down will be exactly equal to the force of drag up. Well, what do we call it when we have forces that are equal? Well, that's a Newton's first law situation. Sum of the forces equals 0. And that means that an object's going to be moving at a constant velocity. Now, the terminal velocity for a human is about 120 miles per hour, based on the average shape of a human being. Can that be affected? Of course it can be affected, depending upon the shape of the clothing, depending upon the surface area of the person. A small human is going to have slightly faster terminal velocity than a large human being. Lots of things are going to come into play, but it's going to be about 120 miles per hour. It does not depend upon mass, because if you remember, acceleration of gravity is the same for all objects regardless of their mass. It's going to depend upon the factors we talked about back here: shape, surface area, and velocity, and aerodynamics. When I was young and foolish, I worked at a flight school. That's what was my college job. It was a great job. I got to flirt with all the pilots and be at the airport all day long. It was a great thing to do while I was in college. And I would watch very often parachutists that would be jumping out over the airport. Now, as these parachutists jump out of an airplane, somebody is always the first one out and somebody's the last one out because the door is kind of small. And parachutists are a wacky bunch. They like doing crazy things like this. They like making cute little circles in the sky and see how many people they can ring up and things like this. So the question is, how do they adjust their velocity as they're falling? Well, if somebody is the first guy out and he wants to slow himself, what he does is he makes himself draggy, big surface area, big surface area, so that he catches lots and lots of air and he slows himself down. If you're one of the last jumpers away, then what you're going to try and do is you're going to try and fly, tuck, get a really aerodynamic shape. And the goal, of course, for many of these people is to be at the same altitude so they can make a cute little shape, break away from each other, pull the chutes, and then they clap, they're excited, and back they go doing it again. Now, most objects that fall through the sky are actually going to achieve a terminal velocity. When you see a leaf falling out of a tree, a piece of paper blowing in the wind that's falling, if they're light, small objects and they're not falling a long way, they're going to actually reach a terminal velocity. There's been many myths or stories about people who have dropped pennies off of the Empire State Building. And I remember in my youth hearing stories about pennies falling off the Empire State Building, and they would go with enough velocity that they could actually penetrate the roof of a car. Well, that would be true if there was no air. But the terminal velocity achieved by a penny falling off the Empire State Building, I don't remember the exact numbers, but it's slow enough that if you got hit with it, yeah, it would smart, and it might even break the skin, but it's certainly not going to go through your skull, certainly not going to kill you. Now, you can mess with terminal velocity if you change the conditions of the air. Back in 2012, there was a gentleman named Felix Baumgartner, and Felix Baumgartner is an Austrian gentleman, and he was the very first person to break the speed of sound while skydiving. Now, the speed of sound is going to vary depending upon air density and temperature. It's typically somewhere around 700 miles per hour, and that's going to vary, of course, like I said, on atmospheric conditions. Well, how the heck can you do this if terminal velocity for a human is right around 20 miles per hour? That's a far cry from that 700. What they did, and this was sponsored by Red Bull, who's into a lot of extreme sports, they actually had to get him outside the Earth's atmosphere. This is a picture of Baumgartner, and this was taken by a boom attached to this little capsule. He rose to a very high altitude of over 120,000 feet, well above the Earth's atmosphere, and then he jumped. So he jumped in a conditions anywhere above about 50,000 feet. You don't have very much air. And so he kept accelerating and accelerating and accelerating and accelerating, got in excess of 800 miles per hour. Once he actually got into the upper regions of the atmosphere, air started slowing him down, and he was actually able to land with his parachute. Remember, drag can be a good thing, catching lots of air, and the air slowed him down from over 800 miles an hour to a speed that he could land safely on planet Earth. Cool and wonderful stuff. That will do for terminal velocity. See you next time.